proceed whenever you're ready.
Okay, so hello everyone, greetings from Munich. So today I will talk about physics-based block preconditioning, which is a collaboration with Alexander Popp and Matthias Mayr at the University of the Bundeswehr in Munich. And I will talk a little bit about how we use MueLu and sparse approximate inverses to do this preconditioning, and an application case would be beam-solid interaction. So let's start with the overview. So next slide. So first, I'm going to talk a little bit about the motivation and the goal, give a short problem description afterwards. I want to describe how a multigrid plays an integral role in our algorithm and how we combine it with sparse approximate inverses. And then in the end, just some small numerical experiments and some conclusions. So let's start with the motivation. Next slide again. Okay, so beam-solid interactions, they actually occur in a wide range of scenarios. So as you can see on the right side, in engineering applications, you would find it in composite materials or in steel reinforced concrete. Also in biomechanics, there are several application cases, for example, collagen fibers in connective tissue. And what we experience with these simulations is that the overall solution time is really dominated by the cost for the linear solver. So what we want to do is we want to achieve scalability through multi-level methods. We will use algebraic multigrid due to its flexibility. But we also will face some challenges like an ill-conditioned matrix due to the discretization and the penalty regularization we will use, which basically prohibits out-of-the-box block smoothing techniques. So just to reformulate, the goal is we really want to achieve a scalable AMG preconditioner for beam-solid interaction problems in penalty formulation. And if we go to the next slide, and then the next one, we can actually see that this results in a 2x2 block structure. So this 2x2 block structure resembles really the beam contributions, the solid contributions, and the coupling terms. And if you go to the next one, you should see a color highlighting. So in green we have our beam degrees of freedom, in blue we have our solid degrees of freedom, and in orange we have our coupling constraints. And the interesting part about this matrix is that we have the penalty parameter epsilon, and if we increase epsilon, we linearly increase our condition number of the matrix. So if we go next, you should see this little diagram that with an increase in the penalty parameter, we see also a linear increase in condition number. And of course, this is not optimal because we want to have a high penalty parameter to really resemble the physics and have a strong coupling. But on the other hand, this makes our matrix more and more difficult to solve in our linear solver. So the challenge here is really that we have a highly non-diagonal dominant and ill-conditioned block matrix due to this penalty regularization. And we might also have a non-symmetric matrix depending on the beam formulation we use. So in the next slide, I will talk about how we use multigrid for this. So for us, there basically exist kind of two flavors of multigrid. On the right side, we have the really fully coupled multigrid method, which means we take our block matrix and we project it onto the coarser levels, which includes the coupling basically of all the matrix components on all levels, also of the off-diagonal terms. And this, of course, requires the near null space to be known for all blocks. And we will later see that for the beam discretization, this is not so trivial to calculate. On the left side, you see a little bit maybe more trivial approach. So we have a block iterative multigrid method, which means we have a block preconditioner on the outside, which means we couple only on the fine level, and then we use independent multigrid hierarchies to approximate the single equations that we have to solve in this kind of block method. And what we will do for now is, if you click next, we will use some kind of block iterative multigrid approach, but we will also facilitate not only multigrid but also upper methods. Depending on the matrix equation we want to solve, it makes sense to also not use multigrid, where the sparse approximate inverse comes in handy at some point. So on the next slide, I will talk a little bit about the implications. So considering the solid discretization of our block system, we basically know from literature how to compute a null space. This is really easy. This is done so often, and we can use an algebraic multigrid method basically out of the box to say they're well established in literature and also well established in MueLu. The difficulty comes in with the beam discretization. So the construction of the near null space really depends on the beam formulation you use. We already have a null space working for Euler-Bernoulli beams, but more broad beam formulations that is still work in progress. There's also the open question of how to coarsen these beams. So if you really have short fibers embedded in a matrix material, does it make sense to do like a harsh coarsening when you just have a few nodes? And the third open question is that algebraic multigrid methods for beams are basically, there's nothing in literature, so it's really state-of-the-art research that has to be done. And what we will do is we do the smooth aggregation for the solid block. We will use some kind of one-level method to approximate the inverse of the beam block. And of course, the penalty, as mentioned, destroys our nice properties of the matrix. So block Gauss-Seidel or block Jacobi does not work here. So we will facilitate some Schur complement preconditioner on the outer level, some block preconditioner there. So if we go to the next slide, we have the starting point that we rely on Schur complement types. So this will include some kind of block value, some Usava, or some simple method, which were already all implemented in MueLu itself, and that you can kind of nicely steer with the XML file. And then with this XML file, we can also select the different block inverses. And what we actually do is we call MueLu once to create our fine level, basically. And we restrict it to that fine level, and then with another XML file that we basically include into this one level restriction XML file, we call MueLu again from the inside to generate the single block approximation. And this sounds maybe a little bit weird now because you could also use TACO for that, but we have internal reasons to do it that way, and also our in-house solver basically uses Xpetra as wrapper for the block matrices, and we don't really have connections to Tira and these things, so that's what we do for now. So on the next slide, you can see just an example for the simple smoother. So we, as it is done in literature, we use some kind of splitting to split our matrix into several parts. And at some point we will face the Schur complement equation in the lower right corner. And there it gets interesting because you have to approximate a hat at some point, which should be easy to invert, and which is an approximation of A. And there are many variants to do this, so you could use just the diagonal and then invert it and so on. And the basic algorithm just outlined is that you calculate your residual, you solve the beam field, so your beam equation, you use that prediction to solve the sure complement equation, for which we use multigrid. You do an update step, and then you basically increment your solution. And if we go to the next slide, you can see that we have several approximations to do. So the first question or challenge is, how do we approximate the sure complement? So in the sure complement equation, you have this A hat that you want to use, which is a easy to invert approximation of A minus 1. And of course, how you do this is governed by the type of block method and physics used, but the common approach and also the implementation in MueLu that we faced is that you can either use a diagonal approximation of the inverse, or you can use some kind of lumping approach where you use an absolute row sum or something like that to get your explicit inverse to calculate the sure complement. And of course, the sure complement highly connects to the approximation quality of the block inverses later on and the overall algorithm. So if you have a good sure complement approximation, I mean, things go good, and if you don't, then things go bad. And what we have seen with our ill-conditioned matrix is that simple diagonal approximations don't work in our case, because the penalty regularization destroys our nice matrix properties. So what we will use is we will construct a sparse approximate inverse of that matrix block, and then we will basically form the sure complement explicitly. So sparse approximate inverse, what does that mean? So if you go to the next slide, just a short introduction. So we will use the matrix graph of our submatrix A, and on that matrix graph we will calculate an approximate inverse on. And the key idea is basically to have a minimization of this kind of residual equation under the Frobenius norm. And of course, if A hat is a really, really good approximation of A minus 1, this becomes more and more zero, and we will minimize this problem over the sets of all sparse matrices with some structure that are known. And the good thing about this, and for the beginning, we will only use the matrix graph of A really, and we can do this in parallel. So we can split this problem or decompose it into row-wise independently scarce problems. So we have one communication step in the beginning, and afterwards we can do this all in parallel, where each matrix row of our inverse is calculated based on a small least scarce problem, which you can do with QR decomposition, something like the serial QR decomposition solver that you also find in the Trilinos packages. And if we go to the next one, we kind of face another problem. So just using the matrix graph of A for the sparse approximate inverse might not always result in satisfactory result. So we kind of use the static pattern selection approach that was also introduced by Joe. So we use recursive powers of our matrix A and use the graph of that. So basically it's just a combination of the rows of the graphs of A, or even simpler speaking, you just multiply your matrix by itself and then take the result and take the sparse graph of it. And you can do this recursively as often you want, but of course your matrix will get denser and denser, and there's always this kind of sweet spot between good approximation and density of your matrix, and of course also calculation time. And additionally, we apply a pre and post filtering of our input graph and of our sparse inverse approximation, which basically results in a quite simple algorithm. So we kind of pre-filter the graph of A to get rid of explicit zeros and small entries. We determine the powers of A depending on the problem we want to solve. we calculate the sparse inverse approximation A hat, and then we do a post filtering of A hat to again get rid of small entries. And what we end up with on the next slide is that we did quite a computational effort in getting the sparse approximate inverse, which basically is a really good approximation of the inverse of one of our matrix blocks. And if you remember block preconditioning methods, at some point you have to solve for the beam equation. And if you already have a really nice inverse approximation of your beam matrix, you can of course reuse this again. And what we do is we have this kind of fixed point iteration where we don't use the diagonal as a matrix as you would do in the Jacobi method. We just use the sparse approximate inverse. So you kind of end up with the sparse approximate inverse smoother, where A hat is basically used to solve this fixed point iteration and is used as solver. And it turned out to be really efficient, that you can really get rid of the errors in the multi-grid cycle, or at least in this one level method already with this kind of approach. And the Schur complement equation again is just solved with the algebraic multi-grid method, and we use ifpack because our in-house code is depending on ePatcher, so we use ifpack's Chebyshev smoother, which offers decent results, but it turned out to be not very robust. And we also use the different flavors of the ifpack edu as smoothers, and they tend to work really well. The problem, of course, is that the setup cost here is quite high. And if we go to the next one, I'll try to be fast and go over these numerical examples. So this is really a minimal working example. So you can see we have this kind of unit cube, and the unit cube is filled with these one-dimensional fibers, and the bottom surface is fixed, tensile surface load applied on the top, and we have around kind of 30,000 solid degrees of freedom and 1,500 beam degrees of freedom. We use one processor for this, and we set some solver tolerances, some material parameters, and we're good to go. And what we are using this really for, you can see on the next slide. So we set up a weak scaling study for this problem. So what I described is our 1 by 1 by 1 domain, and then we scale it up in all directions to basically end up with a 2 by 2 by 2 domain, where we use 8 processors and multiply the degrees of freedom by 8. So because of the weak scaling study, we try to keep the workload of each processor kind of the same. And we also use a fixed seed for this kind of random distribution of the fibers inside the block. So with the bigger subdomains, you will see that the inner part will resemble the smaller problem. It's just bloated up basically. And we will scale this up till a 10 by 10 by 10 domain. So we end up with around 25 million degrees of freedom, and we use 1,000 processors to solve this, which is basically the upper limit of our on-site cluster that we have here. And on the next slide, you can kind of see the weak scaling hierarchy. So on the rightmost column, you can kind of see that the workload per processor, it differs a little bit, but it mostly stays constant over all these different examples. And we will use, or we use Sultan as our domain decomposition method or like package, and we use a geometric bisection approach. So what we want to do is we want to have a spatial close distance between the solid elements and fibers that are on one processor to keep the communication cost low between the evaluation of these coupling terms or the off-diagonal entries of our 2x2 block matrix. And the results are shown on the next slide. So we use Velos as our iterative solver package, and for this one, we use the BiCG step method. And you can see that the solver time increases linearly, which is not optimal. So we hope that this black curve or line is a little bit flatter. But this is just a first attempt, really, and we of course have to do more investigation into this. So for the first part, it's okay, but of course it's not optimal. The same kind of is also true with the iteration count. It's a little bit better. So normally you expect a constant line, but especially for the lower problems, or like for the smaller problems, you can see quite rapid increase in iteration numbers. The good point here is though that for the bigger problems, it tends to flatten out. So we assume that if you go even to a higher processor count, it will be constant. So that would be nice to investigate. But of course, our cluster is already hitting the limit. So we'll have to see how we do this in the future. And with that, I will go into the concluding remarks. So basically, what I've presented is that our application case really is a mixed dimensional modeling between a one-dimensional fibers and three-dimensional solids. And we use Kirchhoff law beam elements for now, which are sufficient for a broad range of applications. So you have seen this composite plate and also the solid block, which kind of resembles a fiber reinforced concrete block. And this beam formulation is restricted to a straight center line in reference configuration. So of course it would make sense to have a more broader beam formulation that can also represent curves in the beginning. And we use a multi-grid block preconditioner based on MueLu. And we kind of also use a self-implementation of the sparse approximate inverse algorithm inside MueLu to approximate our Schur complement equation, and to also use that for smoothing of one of our equations in the block preconditioner. And this is already proved to be a really successful proof of concept for engineering applications, and we kind of have our first week scaling results that go into the right direction. And so as an outlook, on the next slide, we kind of want to extend to other beam formulations, especially Seymour-Reisner beams, which represent not only translations nicely, but also rotations of the beam. And therefore, we also not only want to, what we did so far is only coupling the translations between solid and beams, but you can extend that also to a rotational coupling between the beams and the solids. And you can also go further even to other coupling scenarios, for example, beam to solid contact and things like that. Of course, performance is a big thing. So right now we are only using MPI ranks, so no shared memory or anything related to that. But it would of course make sense in the near future to implement a thread parallelism SPI method to investigate the behavior and computation performance there. We of course want to reduce our preconditioner setup time that I haven't shown because it's already quite high. And we want to investigate and improve the weak scaling behavior. And in the long term, we of course want to have something that is related to a fully coupling multi-grid method. So we really want to project our whole block matrix onto coarser levels and then also reuse the sparse approximate inverse as level smoother on all these different levels. But for that, we have still need to investigate the null space calculation of our beam formulation. And so finally, I want to thank my collaborators, which is Matthias, Mayr, and Alexander Popp. Some references. So parts of the things I presented are already open source and available in MueLu. There's still some things that need to be added, but of course I'm an external collaborator, so right now it's really difficult to get merge requests reviewed and also to get them merged, because not seeing testing results makes things a little bit difficult. I also want to thank my financial support, and if you have any questions, you can of course contact me. So I don't have Twitter or LinkedIn, I just have my mail address. And you can, of course, you're highly invited to have a look at our institute webpage. And with this, I'm open to questions, and I think I stayed in time, so that everything is punctual.
Yep, no, thank you, Max. Yeah, I have questions for Max.
Can I ask what is the difference between the big scale 3 where the time was going up and the one you showed before where the time was not going up?
So I'm sorry, but I think I did only understand the half. So what's the question, why our solver time goes up like this?
Yeah, so there was one plot where there was big scale 3 where you call the third number 3, then the time was going up, and then there was a hit.
Yes.
And the time was not going up.
Yeah, so I'm not 100% sure. The thing is that at some point in our simulation, the problem size gets so big in exclamation marks that MueLu adds another level to its multi-grid hierarchy, and this plays a role and has certain effects, and I'm pretty sure this is related to that. Of course, I'm not 100% sure why it then starts to increase like it was before, but I think this plateau is really connected to this additional multi-grid level. This is added due to the problem size increasing and the course max size you use for your course level. I hope that answers your question.
Yeah. And the problems, the first one, big scaling had smaller problems. Is that what you're saying?
Yeah, kind of, yeah.
Okay, all right, thank you.
All righty, any other questions? Well, thank you, Max. Appreciate sticking around even late as it is in Munich.